This is Deinonychus enteropus, maxing out at around 3.4 meters or 11 feet in length and 73 kilograms or 161 pounds in weight. It is not the most imposing of carnivorous theropods. However, interpretations of its biology and ecology have played a major role in our reimagining of life in the age of the dinosaurs. Unsurprisingly, then, it's excited a lot of popular interest, including a whole bunch of YouTube videos. In this episode of Super Predators, I'm not going to spend a lot of time rehashing what's already been done. You can get that from any number of other videos and documentaries. What I will do is take a deeper look into what the latest science tells us about some of its key features and what these tell us about how this razor-toothed, sickle-clawed predator lived. As always, I'll give you a heads up on where this information comes from so that you know I'm not just reading it off the back of a cornflakes packet. As some of this is based on my own published research, I figure I'm better qualified than most to do this. If this interests you, keep watching. Hi, I'm Professor Steve Rowe. I'm a real paleontologist, and you're watching Real Paleontology. And today we're talking Deinonychus. The name means terrible claw, and there are no prizes for guessing why. Deinonychus lived in North America between around 115 and 108 million years ago. It's pretty well represented in the fossil record, with a number of near complete skeletons found. It's a dromaeosaurid, commonly referred to as raptors, and Deinonychus is quite closely related to another very well-known theropod, Velociraptor here. Deinonychus was described and named by John Ostrom back in 1969. This is widely touted as the paper that kicked off the so-called dinosaur renaissance. Ostrom argued that Deinonychus was a highly active, agile, and possibly warm-blooded beast, in stark contrast to the long-held belief that dinosaurs were slow, lumbering, and dim-witted beasts. So let's get into it. What are the major controversies and what is the latest science telling us? Well, the big questions are, what did Deinonychus eat? How did it catch and kill it? And how did it eat it? Key adaptations that provide clues here are to be seen in the forelimbs or arms, as well, of course, as its skull, teeth, and the very conspicuous enlarged claw on each foot. One last question we will tackle is whether Deinonychus was a highly social pack hunter, as first suggested by Ostrom back in 1969. Okay, so what are its forelimbs telling us? In 2002 here, Kenneth Carpenter presented a pretty comprehensive comparison of the forelimbs in non-avian theropods, ranging from the massive 5-ton T-Rex to a 20-kilogram Coelurus. Deinonychus was also included. Carpenter broke these theropod forelimbs into three categories: long-armed graspers, clutches, and combination grasper clutches. Deinonychus falls in the long-armed grasper group, but interestingly, it shows a capacity unique among all the non-avian theropods included in his study: the ability to rotate its hands inwards, like this dude here. And even more interestingly, this is a feature common to living theropods, that is, birds. Maybe this doesn't sound like a big deal, but it's a very handy trick, so to speak, if, for example, you wanted to flap your wings and fly. More on this later. Now let's talk about its skull and teeth. As you can see here, Deinonychus's skull was long, tall, and narrow, and its teeth were serrated and compressed. Among living animals, its teeth are probably most similar to the teeth of the Komodo dragon. And interestingly, in the first attempt to quantify the bite force of Deinonychus, Francis Tyrion and colleagues here used the Komodo dragon as a baseline against which they compared a wide range of carnivorous non-avian theropods. They found that the lower jaw of Deinonychus was about 80% stronger than that of the Komodo dragons. Now, this might sound impressive, but as myself and colleagues showed using 3D computer simulation back in 2007 and 2009 here, the Komodo dragon has a surprisingly weak bite. So, demonstrating that an animal had a more powerful bite than the big lizard isn't necessarily saying much. But what we also showed is that the Komodo had a clever trick up its sleeve. As you can see here, the dragon goes in to take a bite with its head at an angle. Once it's sunk its teeth in, it pulls back using powerful muscles in the rest of its body and uses this leverage, like a can opener, to tear flesh away from its hapless victim. Bottom line, it doesn't need particularly powerful jaw closing muscles because muscles in the rest of its body are doing the heavy lifting. I go into this in more detail in this episode on Megalania, Australia's awesome giant monitor lizard. More recently, in 2010, Paul Gignac and friends came up with an estimated maximum bite force of between 4,100 and 8,200 newtons for Deinonychus, effectively between 4 and 8 tons of force. This was determined by predicting the force required to make an indentation on a bone purportedly bitten by Deinonychus. Now, this most certainly is impressive for a 70-kilogram animal. In fact, it's comparable to the bite force predicted for Tyrannosaurus rex using the same methodology as Gignac and friends in this 1996 paper. However, what we need to bear in mind here is that we are making comparisons based on estimates derived using different methods. I go into this in some detail in this episode on the world's biggest spiders. A range of different approaches have been applied in recent years, and they all have their pros and cons. One is to stick a transducer into the mouth of a living animal and to try and get it to bite as hard as it can. Problem here is that we can never be sure that the animal was biting as hard as it could, and it's obviously useless for predicting diet in extinct animals. The approach used by Gignac and Co. is interesting, but again, it has very limited application. Firstly, you need to be sure that the extinct animal you're investigating is indeed the species responsible for the indentation, and this doesn't happen too often. And secondly, as with using a transducer in living animals, we can't be sure that the individual that left the indentation was biting as hard as it could. In fact, it probably wasn't. Another problem with the indentation approach is that we don't know whether it was just the jaw muscles that drove the teeth in or whether other muscles were used as well. Anyway, if we're trying to make broad comparisons with a wide range of species, including extinct ones, what's important is that we use the same method for each of them. It's also, of course, got to be widely applicable. And realistically, the only methods we can apply more broadly at the moment are 2 or 3-dimensional simulations using predictions of maximum muscle forces. In a nutshell, my main issue with Gignac et al.'s method isn't that they are more or less accurate. The problem is that it can only give us a very limited range of valid, meaningful comparisons. Unfortunately, in every YouTube video I've seen that's focused on Deinonychus, the fact that the method used to predict its bite force is very different to the method used to predict it in other species isn't mentioned. The result is that Deinonychus's bite force is portrayed as extremely high relative to other predators of comparable size, and this is just wrong. However, a much more comprehensive bite force study was published recently by Manabu Sakamoto here, based on estimation of maximum muscle forces and 2D modelling. At 770 newtons, Sakamoto's prediction for Deinonychus was almost an order of magnitude less than that of Gignac and Co.'s. Regardless of which author had the most realistic bite force, Sakamoto's estimate is much more useful because now we can make meaningful comparisons across a much broader range of species and see how Deinonychus really stacks up. And what his results show us is that Deinonychus did not have a powerful bite. Frankly, quite the opposite. For example, based on my own 2D simulations of other species in this paper here, we see that a clouded leopard, a third of Deinonychus's body weight, could bite 50% harder, and a Tasmanian devil, a tenth of its size, could bite almost as hard. Well, I would say this is no surprise to me. When you look at its skull, it's clearly very narrow, with lots of thin struts and open space. It's lightweight, and in engineering terms, it's what we call space frame. It's a design that minimizes the amount of material used, in this instance, bone. This can be optimized for use, but in a limited number of ways. It's not a skull that is adapted to take big random forces or to give them. The obvious advantage is that it saves weight and energy. The disadvantage is that it needs to be used with a degree of precision, otherwise, it might break. There is just no room for massive jaw closing muscles. Here it is next to the far more robust skull of Tyrannosaurus rex. And there's another obvious difference between the two. The massive teeth of the tyrannosaur are built to take high loads. The more fragile, knife like teeth of Deinonychus are not. They are well adapted for slicing through fibrous material like skin and flesh, but definitely not for pulverizing bone. This brings us to another point. Although Deinonychus does not have particularly powerful jaw closing muscles, it's probable that, like the Komodo dragon, postcranial muscles played a major role. In this 2018 paper here by Angelica Torreses and colleagues, it was shown that dromaeosaurids, like Deinonychus, used a puncture pull technique to remove flesh from their prey. This was deduced from analysis of wear marks on their teeth, as well as computer based predictions of strain. This study didn't actually include Deinonychus, but it did include the closely related Dromaeosaurus, which has very similar skull and tooth anatomy. Now, what about its signature feature, that terrible claw? Well, there have been many potential uses proposed. One of the most obvious is that it might have been used to open gaping wounds and possibly disembowel its prey. This was the method offered up by Oswald in his original description. There have been at least seven so far as depicted in this figure. The most influential have been the interpretations presented by Philip Manning and friends in 2006 and the model proposed here by Denver Fowler and colleagues in 2011. Interestingly, neither of these models envisage the terrible claw as a weapon important in the actual killing. Both concluded that the jaws, not the claws, played the dominant role here. Okay, so what did these authors actually do? Well, in 2006, Manning and Co. built a hydraulically powered robotic leg and foot modelled on Deinonychus and used it to strike a pig's carcass. They found that it wasn't terribly effective at producing penetrating wounds and proposed that the terrible claw was used as a climbing crampon, giving the predator purchase as it leapt onto the back of its big prey from where it would deliver fatal bites. Fowler and Friends 2011 had a different take. They introduced the raptor prey restraint model. In order for this to be valid, we have to accept straight up that Deinonychus had feathers and at least some kind of proto wing. There's no direct evidence of feathers in this species. However, there is pretty much universal acceptance of this proposal. This is because there's indisputable evidence of feathers in its close relative, Velociraptor, and the fact that its forelimb is remarkably similar to that of Archaeopteryx. The authors draw support for their argument from observations of living raptors, like this little sparrowhawk here flapping away to maintain balance while pinning down a pigeon. Fowler and friends conclude that this behaviour may have been an important step along the road to powered flight. Some more recent studies have tested these hypotheses. In 2021, Sylvia Ascari published the results of very wide ranging analyses that included mammals, reptiles, and birds with different claw shapes that correlated with different behaviours. Long story short, her results were most consistent with the use of the claw as a means to pin down the prey, not to climb or slash. Ascari went further to observe behaviour in what is probably the closest living analogue to Deinonychus, the rather eccentric red-legged Seriema of South America. Now, obviously, this is a very different skull to Deinonychus, but its feet possess an enlarged claw on its second digit, as you can see here. The Seriema's other claim to fame is that it's the closest living relative to the extinct terror bird lineage, the subject of this earlier episode. Interestingly, if you give a red-legged Seriema anything that remotely resembles a small prey item, it will repeatedly pick it up and dash it on the ground before pinning it with its enlarged claw and eating it. A later study by Oswald and others in 2023 confirmed this. So the analyses of both Ascari and Oswald give a tick to the use of the so-called killing claw of Deinonychus as a tool to help hold prey down, as suggested by Fowler back in 2011. Another important point raised by Ascari is that the Seriema was observed using its killer claw for other purposes, including grooming and aggressive encounters with other Seriemas. Now, there's one study I haven't mentioned yet. That's this one by Joseph Bishop in 2019. I've left it to last because it's a test of all hypotheses so far. Bishop constructed a digital model, including the leg and foot bones of Deinonychus, as well as the leg's muscles, and he used it to determine the behaviours under which the transmission of force to the sickle claw was maximised. Another long story short, Bishop concluded that of the 7 functions proposed for the claw, the prey restraint model was again the best supported. But it's important to note here that using the big claw to restrain prey doesn't necessarily mean that it had to be used in conjunction with stability flapping, a key component of Fowler's hypothesis. However, 2 of the remaining 6 other functions certainly couldn't be ruled out. A kick to the prey's vital areas, basically disembowelment, and the use of the claw to dig burrowing prey out of their homes. On the balance of evidence, Bishop backed Fowler's proposition that Deinonychus habitually preyed on animals smaller than itself, pinning them to the ground with the aid of its outsized sickle claws, but used its jaws and sharp teeth to do the actual killing. So, where does this leave us? Well, clearly, most recent studies have concluded that Deinonychus probably did not use its killer claw to actually kill, and there's a growing consensus that it was a habitual predator of animals smaller than itself. This has ramifications for the last question I wanted to address here. Was Deinonychus a pack hunter, a social animal? If it was strictly a predator of species smaller than itself, there would seem to be no need for pack hunting. Now, this pack hunting proposition has been around ever since Ostrom described it back in 1969. The remains of at least 4 Deinonychus were present at the original site here in Montana, along with the remains of a big herbivore, Tenontosaurus. And by big, we're talking around 1,000 kilograms, so at least 10 times the size of Deinonychus. I should quickly mention here that although 70 kilos is the most commonly cited maximum weight, my colleague Nick Campione here at the University of New England has more recently published an estimate of 100 kilos. Anyway, Ostrom figured it was most unlikely that a lone Deinonychus could have brought down the much larger Tenontosaurus by itself, and given that there were at least 4 Deinonychus present at the site, the pack hunter hypothesis was certainly not a silly suggestion. Since 1969, there have been other sites found with evidence of both Deinonychus and Tenontosaurus. In fact, the majority of Tenontosaurus have been found alongside the remains of Deinonychus, be these skeletons or just teeth. However, A pretty comprehensive argument against the pack hunting hypothesis was presented by Roach and Brinkman in 2007 here. These guys pointed to the fact that true pack hunting is extremely rare among the sickle-clawed theropod's closest living relatives, birds and crocodiles. They also point out that at the original site especially, there were a heck of a lot of dead Deinonychus. If these were all members of an organised pack that was killed by the Tenontosaurus they were attempting to take down, it frankly suggests that they were pretty crap at being pack hunters. 4 dead Deinonychus for 1 kill is a horrendous attrition rate. They also note that one of them appeared to have the claw of another embedded in its back, rather strongly suggesting that the Deinonychus may have been killing each other. Roach and Brinkman's conclusion was that its behaviour was probably closer to the Komodo dragons than a real pack hunter like a wolf. The Komodo can certainly prey on animals much larger than itself, and it's not unusual for multiple individuals to pile on in a kill. But this is hardly the organised pack hunting that we see in mammalian social predators, and things can get very nasty at a Komodo dragon kill site, with larger individuals quite often killing smaller ones and eating them too. Lastly, Fredrickson and friends here in this 2020 paper analysed the teeth of juvenile and adult Deinonychus to find that they had quite different diets. Again, this is not what we find in mammalian social predators, where the adults feed the juveniles the same food that they're eating. So, what are we to make of all this? Well, before I give you my take on it, can I ask that you please like and subscribe? It'd be much appreciated. Back to it then. Did Deinonychus habitually kill its prey with a literally gut-wrenching sickle-clawed kick? Was it restricted to prey smaller than itself? And was its outsized claw restricted to the role of a restraining tool? Lastly, was it a wily bona fide pack hunter, or was a Deinonychus kill site more like that of the Komodo dragons, a scene of chaotic carnage with every theropod for itself? Well, here's what I reckon. Firstly, on the question of how it killed its prey, straight up, I don't think that this has to be a simple one or the other response. Most living predators use different behaviours depending on the target prey species. For example, living cats will use a clamp and throat hold on big prey and a crushing bite to the back of the skull for smaller prey. Maybe Deinonychus used a kick under some circumstances and a bite under others. Maybe under some circumstances it used both. I think Manning's robotic simulation was really neat, but I'm not entirely convinced. There's a degree of uncertainty regarding the actual shape of the claw. The outer layer of the claw is a keratin sheath, but this is not preserved in any fossils of Deinonychus, and the shape and size of the sheath can make quite a difference, as you can see here in this image of an eagle's claw with and without the sheath. It's also been reported that there's quite a bit of variation in the shape of its claw between individuals. We would need to run simulations encompassing this range before we draw any final conclusions. It would be interesting to see a similar test simulating the kick of a cassowary. This big terrestrial bird, about half the size of Deinonychus, has a large, although far less recurved claw. Yet it is still known to have killed at least 2 people with kicks that can undeniably open fatal wounds. I discussed this further in this earlier episode on terror birds. Also, there's no obvious reason to discount the possibility that kicks were used on smaller or intermediate sized prey. Another thing I think we need to be wary of is that just because a particular structure is not totally optimized for one particular purpose doesn't mean that it wasn't used for that purpose. There are countless examples of this in the animal kingdom. But if we're just talking about claws, then a good example might be the sloth bear, also the focus of an earlier episode. The sloth bear's long claws are best adapted for digging out ant and termite nests, its main source of food, but its claws can and do kill people. lots of people. In fact, sloth bears kill more people than tigers do. And while they often use their jaws too, the claws are their frontline weapons. As reported here in 2022 and elsewhere, these can often cause severe facial injuries, including the loss of eyes, noses, and ears, and in some cases, the scalp can be entirely torn off. Also, although Bishop 2019 concluded that the claw was best adapted for prey restraint, both kicking and digging were the next best supported. It was almost certainly used for other functions too, such as fighting with other Deinonychus. There most definitely are living theropods that use modified claws to settle differences with members of their own species in the world today. As to the argument that Deinonychus was restricted to prey smaller than itself, I just don't buy it. Its association with the remains of Tenontosaurus is just too frequent to be repeated examples of scavenging as opposed to active predation. Lastly, was Deinonychus a social predator, a pack hunter? Now, I know this is a cherished thought, long championed by producers of both movies and documentaries alike, but I don't think it stands up to scrutiny. Aside from being extremely rare among living archosaurs, the presence of multiple dead Deinonychus at a single kill site is far more easily explained by aggression within the species than by defensive maneuvers carried out by the lumbering Tenontosaurus. I think that Roach and Brinkman were on the money, and that although a bunch of Deinonychus likely piled on in the kill of big prey, this more likely resembled the behaviour of Komodo dragons than wolves or killer whales. There you have it. That's my take. Enjoy the rest of your day or night, and you can let me know what you think in the comments section below.